Okay, so yesterday we talked about time. And two words I hope you guys are familiar with now is the idea of relative dating versus absolute time. Relative dating is basically the idea that as you put layers on top of each other, you can then make a prediction as to what was placed there first. I mean, as a silly little example, I'm fairly confident on that the microwave went down first, and then later I put the coffee on top. That's probably what happened, right? And that's just logical, right? I mean, for anything that's piled together, right? Like Chelsea's books right there. I'm fairly certain the black binder went first. Then, based on the looks of it, probably was that black book that was next. And then her, what do you call that? Satchel bag? Sure. The sling bag went on top. That's my guess, right? But is it possible that like she plopped the whole thing down all at once? Maybe, I don't know. And that's the problem with trying to measure the Earth and time is that we can't actually go back in time. I actually joke about that on this slide right here. Is that the age of the Earth is actually a really challenging thing to measure because we can't actually go back in time yet. I don't know. Maybe one day we can. Physicists are actually working on problems on time travel. They're nowhere close yet, but black holes and quantum theory. I don't know. Maybe they'll get there one day. So hopefully these words I have in bold here though are something you know. So let's talk about the first one as a review. Is it okay if I kind of sit here and I can see most of you guys? Okay. So the first one is called uniformitarianism, like the biggest Scrabble word in the world. Someone put that into your own words. What does uniformitarianism mean? Sure. And that really applies to everything, not just volcanoes, right? So the idea is that things that we recognize as happening today, we don't have any reason to believe they wouldn't have happened before. Right? And so the main thing this applies to would be like strata layers. The idea that like, let's try to draw a picture here. The guy discovered all the layers looked like this, and then he found some layers that were sideways. And he was like, that makes no sense. But then he had this brilliant idea. Well, hang on. We have mudslides. We have earthquakes nowadays. Well, what if there was an earthquake a long time ago and a whole bunch of rock that used to look like this all of a sudden fell down? Seems logical. Again, I can't actually go back and prove it, but it sure, at least it's based on the evidence we have, it sure makes sense, right? And so that's uniformitarianism. The law of superposition then is the laundry basket idea of, well, stuff at the bottom is probably old, and as you work your way up, it's probably younger. Again, probably. The last one is the idea of half-life, and that's probably the hardest one here. Basically, the idea is that, I'll make a new slide here to do our review, is that what ends up happening is compound A, whatever it happens to be, will radioactively decay into compound B, but it takes a long time. And so it might take, let's just use a simple example, it might take 100 years for half of A to turn into B. And so that would mean that if we made kind of a table here, after 100 years, you have 50% left. And then after 200 years, you'd be down to 25%. And after 300 years, you'd be down to 12.5%. And slowly but surely, this is going to be like 6%, give or take. Slowly but surely, you're losing your A because your A is turning into B. And I had a picture in our notes of, I think it was a gopher. And you can literally see the picture in the notes of the gopher like decomposing slowly but surely over time. Right? However, this is based on the idea of uniformitarianism again, is that we assume that we can recognize how humans decompose now. We assume that life has always decomposed at the same rate millions of years ago. Again, I'm not, hopefully you guys don't think I'm trying to say that it's not true or anything like that. I'm just saying this is what science is. Science is basically trying to make predictions and hypotheses based on the data you have. So based on what we recognize, this seems to make sense. So the idea then is that let's say that I find that you have, I don't know, let's say 20% of A left. Well, if there's only 20% of this left, how much of the daughter nucleus did you make? Yeah, they add up to 100, right? But it's this guy you got to focus on. How many times does it take to cut in half to get to 20? Well, cut it in half once, it's 50. Cut it in half twice, it's 25. Cut it in half again, it's down to 12 and a half. We want 20, which is like somewhere in the middle. And so you use this little chart out of your book, and I'll give you one on a test. It's a little chart like this. What you do is you look for where the 20% is, and 20% ends up being at, I think it's about like 2.4 half-lives. And So then you say, well, if a half-life is 100 years, take 2.4 times by 100 years, it must have been 240 years old. That's kind of the basic idea. It's actually not all that hard. You really just need two things. One, you have to be told how long the half-life is. You need to know that. And then two, you have to know what percentage it is, but the percentage has to tell you like whether you have one half-life or 1.5 half-lives. All you do is you just times those numbers by 2. I'll tell you right now, I do give you one question on both your quiz and your final exam on this concept. If you want practice, I'll find you more practice. Anyways, let me go back in my notes here then. Based on this information, geologists think they know how old the Earth is. If that they believe, based on the evidence we have, we know the Earth is about 4.5 billion years old. That's about how old the oldest rock formations we can find out. But today we're going to focus on the internal structure of the Earth. And if that makes sense to you guys, I'm talking about like what's on the inside. As a silly example, anybody ever have like one of those like super awesome bouncy balls? You're like a little kid, you bounce and it goes fleeing everywhere, and then you ask yourself, I wonder what it's made of. Well, the only way for you to know what it's made of is to literally take your bouncy ball and like cut it in half and look at the inside and go, yeah, that's what's on the inside, right? Only the problem with Earth is we can't exactly cut Earth in half and go look in the middle, right? Even the deepest mines or the deepest like caverns that we have are still only like literally miles deep. And we know, due to some math calculations, that the Earth is like thousands upon thousands of miles across. Now, like, if I were to talk about like digging inside the Earth, like we hardly even scratch the surface based on how far we go. Right? Like, if this is a picture of the Earth, now this is say north, this is south, and I wanted you to dig inside the Earth, we might get maybe that far. And that's probably still actually way too far. Because like how far it is literally through the Earth is ridiculously big. So again, my slide here then is the internal structure of the Earth is also a challenge to know with certainty because we can't go through it. But today I'm going to show you the evidence we have and then the assumptions we make based on that evidence as to what we believe the inside of the Earth looks like. Does that make sense? So that's today's lesson. It's about what is Earth made of. Now before I start, I want to talk a little bit about rocks. This is something that I understand is in like junior high science, so you might know these words. We're not going to focus on them a lot, but the words are sedimentary, igneous, and metamorphic. You guys ever heard those back in like grade 7? Honestly, it's been years, so let's just do a quick recap. Sedimentary rocks, I've got a picture here actually. Sedimentary rocks are often ones that have kind of like layers to them. Igneous rock is kind of like what happens when lava or magma cools. And then metamorphic rocks are ones that are in the middle of changing. And I've kind of got this picture here of them, where there's these different rock cycles. I don't know if that helps at all. Why don't I give you a second here to write down the definitions? I found a YouTube video that you'll laugh when you see it because it's totally lame, but it'll hopefully show you the three rocks that are igneous. So just give you a second to write down what you want first here, and then I'll come back. Sedimentary, igneous, and metamorphic. Oh, sedimentary is often like in like the ones we see that have like this inside. Here, why don't I find that video? I'll even play it twice if we have to. This is a teacher who made this for like his class. It's ready to rock?
Okay, so there's many different types of rocks, right? There are some that may be familiar to us, and others not so familiar. Which begs the question, why are there different types of rocks? Well, it has to do with the processes of how they are formed. And there's three main processes. There's melting and cooling, weather and erosion, and there's also heat and pressure. The first process
you guys are familiar with are probably sedimentary rocks because they're mostly on the surface. So if you go outside and find a rock in sedimentary, sometimes you'll see them though because as they've been like buried deeper and deeper, you can kind of like see those lines that kind of go across them. Anyways, that's sedimentary. I'll let him keep playing this video first. Shut off.
The final process is heat pressure. Rock deep in the ground becomes soft and is eventually squeezed to form metamorphic rock, like this rock, called gneiss. These processes cause rocks to change. Igneous can turn metamorphic, metamorphic to sedimentary, sedimentary to igneous, or igneous to sedimentary, sedimentary to metamorphic, metamorphic to igneous, and these rocks can even change back to themselves as well. So this can bring us to the conclusion that all rocks can form into any other type of rock. Whoa! And these processes, with the help of lots of time and these different patterns, form the famous rock cycle. Thanks a lot, and rock on.
I need to watch the rest of it. It's kind of silly. Here, let me go back to that picture here. He talked about three main things. I'm going to write them on here. One of them was either heating or cooling. Another one was called erosion. And the other one was pressure. Those are basically his three things. And that's how you can change rocks from one to another. So I hope you guys can see this picture on the screen well enough. If not, it's in front of you as well. Let me try to walk you through the idea here. Imagine that you have some surface rocks, right? Some just backyard rocks. What happens if, like, say, the wind or the rain batters them for years? Which of these three processes is it probably going through? Yeah, erosion. If you go to a river and you look at all the rocks in the river, are they going to be smooth or jagged? Smooth. Because slowly over time, the river will have actually like smoothed out the edges as the water runs over them. And that often happens in the sedimentary process, where the sedimentary rocks are usually undergoing some sort of erosion process as they're getting broken down. Now, eventually those rocks get broken down so small, like we're talking smaller than gravel, we're talking like really, really tiny amounts, and maybe they get buried over time. That's what's happening in this picture here. Imagine that you've got rocks that are on the bottom of the ocean, and they're nice and smooth because they've slowly been eroded away to basically just fine particles of like dust. Probably the best way of thinking about it, think of sand, right? It's basically sand. Isn't sand basically tiny rocks? Well, slowly but surely, those slowly but surely, these rocks that are on the bottom of the ocean floor, they get buried, buried, buried into layers. Makes sense? Well, what is happening as these rocks are getting buried into layers? Well, imagine a dog pile, right? I don't know, maybe a rugby scrum of some kind. The person that's on the bottom, he's going to have a lot of pressure on him. Makes sense? And slowly but surely, all those little itty bitty rocks get squished together. And that is metamorphic. You can kind of see that in this picture right here, is that as they get built up, more metamorphic rocks. Now, another thing happens though. We believe, and I'll show you the evidence for this later, but we believe that deep inside the earth, it's actually quite warm. Well, you know what ends up happening is sometimes you can heat up rock. And so what could happen is your sedimentary rocks could get heated up, or your metamorphic rocks, the ones below the pressure, they could get heated up. And eventually you're actually talking about them like becoming liquid. You could actually have liquid rock, which, again, I talked about this last day. To me, I'm thinking of like Samwise Gamgee trying to throw the ring into Mount Doom in The Lord of the Rings, right? Where it's like, it's literally this like lava, right? And we recognize that. Ooh, what did I just do? There we go. We recognize that inside like a volcano, right? And maybe those liquid igneous rocks, maybe those actually eventually flow through a volcano and erupt around the side. Well, what happens when they eventually cool is now you actually have a rock, though. Does that make sense? Like you need the magma to actually cool back down, and that's the third type of rock. Well, what happens to those rocks slowly over time? Well, all of that volcano eruption eventually gets weathered due to erosion, due to rain and wind, and the cycle continues. Does that make sense? So those three types of rocks, we recognize that those are the three that we kind of can see based on how far down we can dig. So we can get as low as the metamorphic, the igneous, and the sedimentary are usually the ones on the surface, more or less. Does that make sense? Okay. This slide right here just has some pictures kind of talking about them. If I can point out some of the basics here, the sedimentary ones are the ones that get compressed. They're formed by weathering them, but slowly but surely they're going to get compressed. Well, how are they getting compressed? By pressure. Dog pile analogy, right? So metamorphic rocks are the ones that all of that sand has basically got squished and squished and squished and squished, and it made a metamorphic rock. Okay. Igneous then are when it's now in a molten form due to so much heat. The extreme heat causes you igneous rock, although maybe it's maybe better not to think of it as a rock yet. It will be a rock once it cools down. So, anyways, that's the evidence we have of what's inside the Earth. So if I use the same analogy of trying to figure out what's on the inside of your little bouncy ball, all we really know is basically what's at our surface. But we do recognize that some of them are below the surface, even quite deep. Now here's another piece of evidence we have as to what's on the inside of the Earth. We don't think there's like a little man with a flashlight in the middle of the Earth, right? Like we have deeper theories. One of them is based on something called the drill core, okay? Where literally what you do is you basically drill down as far as you possibly can, and then you bring up a cylindrical kind of like pattern of what was inside. Does that make sense? So I don't know, like I think of construction when I use a drill bit to like drill into something, it was try to bring it in there, right? When a drill bit's going around and around in circles, it's really just grinding things up. But if we can find our way to like grind around it and then pull the middle out, it'd be like coring an apple, right? And so here's a picture I found online of a drill core. And hopefully what we can do is if this is the top and if this is the bottom, then we assume that the top is the newest and the bottom is the oldest. And hopefully we can kind of figure out, well, what kind of rocks are down at the bottom, because that will hopefully tell us about what Earth would have been like previously. Does that make sense? And not only what Earth was like previously, but like what's inside the Earth. So now, as a brief aside, do you guys know why we take drill core samples often in Alberta? We're trying to find oil, yeah. That's really the overlap here, is that often we're trying to drill for oil, and you're digging down deep trying to figure out, hey, is there oil down there? Now, one of the downsides to that is that you're just kind of randomly going, hey, is there oil over here? Let's dig down really deep. Hey, is there oil over there? Right? And like, that wastes a lot of time. So I'm going to show you guys some ideas later as to how drilling companies figure out where to drill. We're kind of going towards that. But I mean, that would be one of the things they do is they dig down really deep trying to figure out, is there oil down there? The word we use for that is right here. It's called a petroleum trap. Okay, but I mean, basically in your mind, think of digging for oil or natural gas. Okay, petroleum trap. Okay. And I've got some pictures on the next couple of slides here trying to describe this. But I'll give you a second to write down petroleum trap first. I mean, honestly, doesn't the words kind of make sense? Petroleum, isn't that just kind of a fancy word for gas and oil? Trap, literally it is trapped in the earth. And we want to get it out because we burn it. I'm going to flip back and forth between two slides. I want to use the picture on this next slide here, and then I'll come back if that's okay. So here's the picture. This is the picture that kind of describes how we believe oil ended up so deep underground. It was actually during the Devonian period of time. I wrote that on the previous slide, which is basically right around when the dinosaurs are believed to have existed, around that time frame. Here's basically the idea. There would have now been living creatures on the Earth, and all of those living creatures would have more or less been underwater. And eventually living creatures would die. Right? And so what ends up happening is these creatures are now dead, and they're lying on the bottom of the seabed. And so there's dead, I mean, I don't know, I guess for right now, just think of like seaweed and plankton and like oozy, gooey stuff. We're not really talking like fish yet. We're just talking like bacteria. And all that bacteria dies. It's all laying here on the bottom of the floor. And so we call that organic matter or plankton. Okay? Well, eventually, the dead stuff right here ends up getting buried by a layer of rocks. And eventually another layer of rocks and another layer of rocks. And so you guys can see in this picture right here, the dead layer of stuff is this one right here. But a new layer went on top of it, and a new layer went on top of it. And eventually, maybe even enough rocks came by that the water is now gone. And now eventually it's got built up to the point where you've got, just land everywhere, like in Alberta. But you know what's ended up happening is there's a rock down here, and there's rock up here. And the word we use is called impermeable rock. We've talked about the word permeable membranes when we did a quick review of Science 10. Permeable means stuff can go through it. So what does impermeable mean? Stuff can't go through it. And so literally that's why it's called the petroleum trap, because below it is rock that oil can't go through, and above it is rock that oil can't go through. And right about here, you've got an oil well. And an oil company decides, hey, I want to try to get to that oil well by digging through the rock. We send a big pipeline down through there. And maybe you've seen some of those pictures of those like hammerheads that try to like suck the oil out of the ground. So if I can go back to my slide here, I'm going to read off of this here. Basically, the idea is that hydrocarbons were created over thousands of years as sediment got pressurized through the porous rock. So the dead plankton and phytoanimals and whatever it happened to be, phytoplankton, bacteria, all that dead stuff, it got squished through porous rock, but eventually it got stuck in the impermeable rock that's down below. And I think that's what's in this picture right here, is that these bottom ones right here is impermeable rock. It couldn't get squished through it anymore. And then it got trapped from about, 500 million years ago is basically the idea. Does that make sense? So anyways, we're able to then drill for oil. And that's not really the point of this lesson, but it does lead to how we know more about Earth. So I'm going to scan ahead here. Oil companies then want to try to figure out, well, where should we drill for oil? Because otherwise it's just kind of random. You just go, well, I'll drill here, right? And unless you come across some prospector back in like the early 1900s who goes, I struck oil, right? They're digging in the ground with their pickaxe, and all of a sudden oil gushes up. You kind of get the picture I'm kind of painting here. Unless you come across one of those scenarios here, well, how do we know where to drill, right? So what they do is they use something called seismic waves. And seismic waves, you guys will recognize this more, we actually encounter them through earthquakes. Okay? Earthquakes cause the ground to literally shake and tremble. And so they can occur from earthquakes, but we actually use explosives to make them. And so oil companies will actually set off explosives. And here's basically the idea. I've got a picture. I don't got a picture. This was the picture I was going for here. It's not a great picture, so I hope this makes sense. What they'll do is they'll set off explosives. They'll blow something up. And what's supposed to happen is a shock wave will then go through the ground, and eventually it's going to hit that rock. Remember that impermeable rock it can't go through? And then the wave will hit the rock, and it will bounce back. And ideally, you're going to get some sort of like internal picture of what Earth looks like. And they call it a seismogram. And I'll try to find you a better picture later, because I realize that the one I threw in this notes here doesn't look all that well. But basically, it tries to measure what Earth looks like by shooting vibrations through the Earth. And either vibrations go through or they bounce back. And the stuff that bounces back or goes through hopefully gives you a picture of where to maybe drill for oil. So this is actually a picture of one of those devices. Anybody ever seen the movie Ocean's 13? The third of the Three Oceans movie? Yeah, okay. As a way of robbing the casinos. You guys ever seen the Ocean's franchise? You guys know, like Brad Pitt, George Clooney, they try to rob casinos. In the third of the three movies, they need to try to find a way to get everybody to leave the casino. And the problem is that compulsive gamblers don't usually like to leave the casino. So what they did is they simulated an earthquake by like having some drilling apparatus nearby, and they caused the drill to like make the building shake. And then based on the building shaking, everyone was like, "Oh, there's an earthquake, everybody out," kind of thing. Anyways, they used a machine like this in Ocean's 13. If you need a movie to watch on Netflix. So this is a seismograph, and basically what it's doing is it's sitting on the ground and it's measuring how much the ground is vibrating. Okay, because really what's happening during an earthquake Or when you set the explosive off, is the ground is supposed to vibrate, right? The more it vibrates, the more that this little needle kind of thing goes up and down. I got another picture here of kind of what's supposed to happen. Right here, there's really no vibrations in the ground. And then here, well, now the ground was shaking, right? And then here, it was shaking a bit more. And then hopefully this makes sense right here. Clearly, here the ground was shaking the most. That's an earthquake. Does that make sense? So anyways, what oil companies will do, if I can go back a few slides here, is they're then going to set off their own explosives because they can't just hope for an earthquake, right? I hope it earthquakes today. It's not going to work, right? So they set off their explosives. The explosives send out some waves. As the shock waves bounce off of stuff and reflect back, they try to make a picture of it. So the words I need you guys to know are seismic waves are the shock waves we send through the earth. Seismogram is the picture that you get of it. And a seismograph is this device right here that makes the picture for you. So really, they all just start with seismo. So you might be asking yourself, Chris, this doesn't help us get what's deep inside the earth, though, right? Because this is really only just on the surface of the earth, really, right? Like this is a few layers down, but how do we know what is deep, deep inside the earth, right? And that's where earthquakes come in. But if you guys kind of get the concept, companies will do the seismograph stuff to try to find oil, but once in a while there will be earthquakes. Now, we don't actually live anywhere close enough for there to be earthquakes, but anybody know where a really common place for earthquakes to occur is that's relatively nearby? That'll work, yeah. China, Japan is one. I was actually meaning even closer by. What did you say? Yeah, California. Yeah, California is actually a really earthquake-prone place. My wife's family was actually in the States during an earthquake in California, and so it's actually a really common place. There's the San Andreas Fault. Ever heard of that before? And so that happens randomly, though, right? So unlike here, where they're purposely setting off explosives, once in a while there will be a real earthquake. And then the good news about there being an actual earthquake is that that is massive. And the shock waves from an earthquake are actually so big that they can be detected on the other side of the earth. Okay. I'm going to draw a quick little picture here. What we're aiming for when you're drilling for oil, where's my new slide here, is that, here's the earth. And here's us standing on the surface of the earth up here. And the oil might be, this far underground, and we want to know that. So we set off explosives, and we get some shock waves that, bounce around up here. But when an earthquake happens, it is so big that the shock waves can literally go through the earth, and you can actually detect them on the other side of the earth using this machine right here. Now, if you were looking at the vibrations, you're probably talking little bitty vibrations on the other side of the earth because it traveled a long ways, as opposed to the ones that are nearby that are very, very big. But it's detectable. And that's why we have to talk about this, is that how those waves travel through the earth gives us a clue as to what Earth is made of. Does that kind of bring me to the point of my lesson? Because this is kind of the whole point, is that the earthquake waves that we get when we get earthquakes, depending on how they travel through the earth, tells us what's inside, or at least we think tells us what's inside. Okay? So the first thing I'm going to talk about, though, is the different types of waves that earthquakes make. And I'm going to do a quick little demo up here. Can you guys come to the front of the room? I'm going to use my spring here. So can you guys come up here and just get out of your desk for a few seconds? Chelsea, you're the first one up. I'm volunteering you. Can you hold that side for me? Okay. So this is a slinky. And a slinky is an excellent way to try to show different waves that can take place. Okay. There's actually 3 different types of waves that take place during an earthquake. The first type of wave is known as a P wave, which is what's on my slide right here. It's called a primary wave. And here's how it works. It looks something like this. See how I'm making some pulses? And these pulses, they happen to travel relatively quickly. I mean, you guys can see they're kind of dying about halfway from me to Chelsea. There's a lot of friction between this and the floor, obviously, right? But if this was an earthquake, no, I screwed it up entirely, didn't I? This was an earthquake. It's quite powerful. There's like a pulse that would travel through. And those pulses, can you guys see how there's like compressions right here? Okay, that's known as like the initial warning for earthquakes, because those aren't actually very dangerous, but they travel really quickly. That would be like the initial little like right here that you might pick up. It's called a primary wave. And I've got that on this slide right here. Okay. These travel the fastest because all rock has to do is basically squish and then expand, squish and expand, just like you see here. And here's the important thing I need you to know. These go through solids, liquids, and gases. Doesn't matter what phase of matter it is, these waves always travel. But there's a second type of wave called an S wave. And I think you guys will remember this as an S wave because here's what it looks like. It goes like this. And it kind of looks like an S, right? Can you guys kind of see how there's kind of an S in there? Now, these ones are slower, right? See how long it's taking that for it to get over to there? These ones actually work a little bit faster. I can't show it very well, but these guys are actually slower. And what literally happens is the rock has to go up and down and up and down, kind of like a boat on the ocean. You know how you're going to rock up and down and up and down? The first one's actually just a push. This one is a side to side. Okay. Now, one of the differences here, though, is that S waves cannot pass through liquids or gases. And the reason why is you literally need rock to go up and down and up and down. But if it's a liquid or a gas, the gas won't necessarily do that. So they can either go up and down or side to side, and literally the rock changes shape, which is why earthquakes are quite dangerous, because although this pulse might hurt a little bit, I mean, if I put, my board right here and I pulse it, that's not so bad. But if I do this, see how it's getting constantly battered and beaten, right? That's going to cause a problem as well. So the words I need you guys to know, and you guys can probably go sit back down now. Thanks, Chelsea, for holding that. So let me go through these slides one more time now that you guys are sitting in front of them. The first wave is known as a primary wave, and it's literally a pulse, okay? Like, think of like a sonic pulse. I don't know if you guys know much about how sound works, but that's actually how you guys are hearing me right now, is that I speak and air molecules will actually compress and expand, and that's why sound can actually travel through air. Does that make sense? Right? If I were to wave this paper right here and go side to side, did those air molecules hit you, Chelsea? Might be doing this? Well, no. But you know what? If I were to give you a big one-time blast, think of like a superhero in the comic books who has like sonar pulse, right? The one-time compression blast, that's a little bit different than the side-to-side stuff. You know what I mean? So that's actually how sound travels. It's through these compression waves called P waves. So again, the important thing I need you to know, though, is that they go through all states of matter, which is why we can actually hear. The second type of wave is the secondary wave because it comes afterwards and they're slower. And it literally involves the rocks going up and down, cracking back and forth. Okay? Now, this is why this is good news. These only go through solids. They can't go through liquids and gases. I don't want to give away the whole goal here, but this is how we think we know what the Earth is made of. Because we think that there's a solid core in the middle of the Earth and that there is a liquid ring around it. I actually have the picture on your progress log here. The belief is there's actually a solid core in the middle and there's liquid magma all around it. That's the belief. But we can't actually go there. But based on how waves travel through the Earth during earthquakes, it gives us clues. Does that kind of make sense where this is going to go? So the words I need you guys to know then are transverse and longitudinal. Okay, the ones that go up and down are called transverse, and the ones that go like push, 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 push are longitudinal. Yeah. So secondary ones are transverse, and primary ones are longitudinal. I probably could even write that on the previous slide. So the ones that go so the burst waves are longitudinal. The back and forth ones are transverse. Now, don't have a slide for the next one, but there's actually a third type of wave. I'll give you a second. I think you need to give you time to write down still, though, don't I? I'll wait a second here. These waves, I gotta point out, these waves are though inside the Earth. Because really what's happening is these are waves that are all happening underground. Does that make sense? There's actually a third type of wave. I don't have a slide for it, but I do have some information on this picture here. There are primary waves, which are the ones that are burst, 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 burst. Then there are secondary waves. You see they're bigger, where they go side to side, side to side, but that's underground. Eventually, the secondary waves and the primary waves will kind of merge, and they'll make what's called surface waves. And that is where the top of the Earth all of a sudden starts to shake up and down. Because these secondary waves are actually still where the inside of the Earth is vibrating. Does that make sense what I'm saying there? So primary waves are the burst waves. Secondary waves are the side-to-side waves inside the Earth. And then finally, you've got your surface waves, where literally the Earth's crust, the top of the Earth, is actually starting to shake. And I've got a slide talking about that. Can you skip ahead here? Can you guys find this slide here? These are the three types of waves. I'm sorry that it's blurry on my screen, because I don't think it's great. Can you guys see that okay on your notes, hopefully? It's a little blurry here, I find. So here's the three types of waves then, if you can follow along. Primary waves can travel as fast as 6 to 14 kilometers an hour. So they're actually relatively fast, because your secondary waves are slower and your surface waves are even slower than that. These guys are the ones where it basically is, it's a push, a push, a push, a push, a burst. These ones are the ones that go up and down, kind of like a wave pool maybe does. Well, these guys are when they combine and they happen on the top layer of Earth, and they're what actually causes the ground to shake. Okay. So it's actually a good thing about earthquakes. There's actually warning for the worst part of earthquakes, because what ends up happening is as soon as one of these machines right here recognizes primary waves as happening, then you know that there's secondary waves coming next, and then after that, now you know that actually the big up and downness is coming. Does that make sense? So you actually have a little bit of warning, not a lot, but a little bit of warning for earthquakes. Let me go to this slide here. This is this is probably the most important slide of everything we're going to talk about today then. Our whole goal then is to figure out, well, what is Earth made of? Because we can't cut it open and just go inside, right? So if you can find this slide right here, it has to do with this idea here. Only primary waves can go through liquids and gases. And because of that, here are two possible models of what Earth looks like. If Earth truly was exactly the same all the way through, imagine Earth was just like a solid all the way through. Well, what should happen is that right here, when an earthquake takes place, you should receive waves here and here and here and here. And so if this right here is like, say, Alberta or Canada, then over here in New Zealand, on the other side of the world, you should be able to register those waves. It's going to take a while for them to go through the Earth, but you should be able to register them. Does that make sense? That's not what happens. What ends up happening are there's what's known as shadow zones, where some waves go through, but other waves they can't. Remember how those S waves, they literally can't go through anything that's not solid? Well, we believe that there is a liquid core inside the middle here. And what ends up happening is, as a wave goes out like this, you would get both S and P waves, because all the waves can go through. But in this location right here, so maybe this is China, but then this right here is, I don't know, Argentina. I don't know, I'm making up ideas here. If this is Argentina right here, what ends up happening right here is that only the P waves can go through, and then the S waves, there aren't any. And so you would think that if the surface was just normal all the way through, you'd end up getting all of the waves all the way around here. But what ends up happening is, in this section right here, you have what's known as the S wave shadow zone, where you get S waves over here. So S ends up here, and S ends up here, and S ends up here, and S ends up here. That makes sense? And P ends up here and here and here. and here and here and here and here, but you only get P right here. So the only logical explanation then is that since you can't get S waves through here, well, there must be some liquid stuff inside. And that's why we believe that the Earth contains liquid magma somewhere on the inside place. Also, based on the way that the waves bend, you guys can kind of see, this picture is not great, but can you see how the lines kind of go, they went straight, and then it bent for a bit, and then it bent back, and then it bent again, and then it bent again? That's called refraction. And we can actually show refraction in other sorts of ways. Probably the best way of describing refraction is the fishing conundrum. If you are standing on the surface of the water and you want to try to hit this fish that's down here underwater, that's a fish, by the way, please don't laugh too much. Your brain thinks that the fish is actually over here. And the reason why is that light will actually cause water to bend. You guys ever seen that before? I don't know whether I can make one here real quick with like a glass cup. Maybe you ever seen the one before where you put like a cup full of water and you put a pencil in the cup, and what you end up seeing is the pencil's up here, and then all of a sudden like the pencil's like over here, and it looks like it kind of like bent. That's refraction. Because really what ends up happening is light waves are bending due to different surfaces. If I go back to that slide right here, that's what's happening right here. They believe, based on the fact that waves are bending a little bit, this wave right here should have ended up over there. But because this wave didn't end up over there because it bent a few different times, that leads to our guesses about what the inside of the Earth is made of. You guys able to follow that? So, can we go deep inside of the Earth? No, not possible. Okay. But do we think we know what's inside? Yes, it's based on earthquake waves. Primary waves go through everything. Secondary waves do not go through liquids. So when you're looking for earthquake waves on the other side of the Earth and you don't find any secondary waves, we assume that it must be made of liquid or gas inside there. Does that make sense? And depending on how they bend, we then think that the Earth is composed of different materials. So I'm going to finish off. We're almost done here. I'm now going to end by summarizing what geologists believe the Earth is made of. Okay. So now we've talked about the evidence for it. Same thing with time. We don't actually know for sure, but we're pretty sure. Okay. So the first word I want you guys to know is called mantle. And mantle is basically like the idea of what most of the Earth is made of. Here's a slide that's got all the words on it. The main part of the Earth is called the mantle. Okay. You guys ever have jawbreakers? If you could cut a jawbreaker open, sometimes there's like different layers inside. Like the main part of it would be the mantle. Or a better example, an egg. You guys ever hard boil an egg? The white stuff would be the mantle. And then you know that like the yolk in the middle, the yellow stuff? Well, then that would be like the core. So here's what we believe. We believe there is a solid core in the middle. Right in the very, very, very middle, there is a solid core. Surrounding the solid core, they believe is liquid. Which kind of makes sense based on what we know about rocks. Don't forget, what we knew about our rocks was there's igneous, metamorphic, and sedimentary. Right? And we believe the igneous ones are the liquid ones that cool off as magma, right, through volcanoes. So we believe that there is liquid right here around a solid core. And then we believe that there's basically the main core. And the main core consists of a couple of different layers. So lots of words here you need to know. The first one's called the crust. If you're using an example of an egg, the crust would be like the shell of an egg. It's literally just like the topmost area, which honestly is about as far as we can even cut into the Earth anyways. So the crust is like the very, very, very top layer of the Earth. And it has a special name though. We call it a lithosphere. Okay. A lithosphere is a crust, and the crust is basically just the topmost layer of the Earth. It floats on the mantle, and that mantle, the main part of the Earth, is called the asthenosphere. And then below that is the mesosphere. So basically there's three different spheres I need you to know. Lithosphere is like the shell of an egg. Maybe I'll use an egg as an example. This is like the shell of an egg. Then this stuff right here is the white of an egg. Yeah. And then this is the inner core, that's the yellow of an egg. So that's your three layers. Crust or lithosphere is the outside. the mantle is the asthenosphere, and your core is your mesosphere. As we go down from litho to asteno to meso, now we're getting down into where we believe our cores are. Okay. Such is the terminology we use. Feel free to write out as much as you need for it. I kind of picked a picture on your progress logs to kind of illustrate it. So lithosphere, asthenosphere, mesosphere, core. Well, actually, around the core, don't forget there's the liquid we believe that's around it, too. I'm almost done here, so I want to give you guys some work time today. One of the things that we know then, or that I guess we think we know, I hate to say no for sure, because that's not how science works. Science is always developing. But we know that Earth is actually a collection of crustal plates. I don't know if you guys have ever seen this picture before. This is where I'm going to end our lesson here. I'm going to talk more about earthquakes. If I can, I'm going to flip a slide. I'll come back again here. I want to go to this picture right here. Anyone ever seen a picture like this before where Earth is believed to actually be a whole bunch of different plates? And we talked about how California has a lot of earthquakes. It's because right here and right there, there's a small little itty bitty plate right off the coast of California. And as these things move next to each other, what ends up happening is all of our plates, we believe they're moving little by little by little. They're just slightly moving. I believe it's like 2 centimeters a year. It's hardly even noticeable. But eventually they get stuck, and they get stuck, and they get stuck, and eventually it almost has to burst, and then that's where like the big release of energy comes from. Does that make sense at all? And so these are the known plates. There's like a big Pacific Ocean plate, and one of you guys pointed out that Japan has earthquakes. One of the reasons why is that the boundary of the plate right here is right by Japan. And the boundary of these plates right here is actually right over here by California. Now, where plates meet, we have a name for that, so I'll go back a slide now. They're known as faults. A fault is basically where two plates are sliding beside each other, side by side. And over time, if they don't actually move and they get stuck, it can eventually get released. A couple centimeters every year. And eventually, they get stuck, and all that energy gets released all at once as an earthquake. So, you know how I gave the example of an egg? It's actually probably a poor example. It'd probably be better to give an example of a hard-boiled egg, and then the shell got cracked, but it's still intact. Does that make sense? So imagine a hard-boiled egg, and then you like go crack it, but don't start peeling the shell off. Okay, the shell would be the crust, but like there's all these little jagged lines around it here, and they can kind of move around a little bit. Okay, that's what we're believing what happens here. So I think I'm almost done. What do I have left? 2 slides left. So here's my last slide of words. When an earthquake happens, you kind of need to watch me use my hands here. What they believe happens is something called subduction, where you have 2 plates, and they're supposed to move next to each other. But what ends up happening is one plate starts to go underneath another plate. That's called subduction. It's actually how we believe mountain ranges formed, where you're supposed to have 2 plates come like this, and eventually they start to tip up. And that's how mountains come together. Plates are supposed to arrive, and then this happens. You see that? Plates are moving. They come next to each other. The faults meet, and eventually one goes down below, one goes above, and this right here, I got a mountain range. So as that subduction happens, it puts a lot of strain on the 2 plates. And eventually the energy gets built up, and it gets released to what's called a focus. The focus then is the initial cause of like the breakage for the earthquake. And I got a picture here. A focus is going to happen deep under the earth, where really this plate right here on this side and this plate right here on this side, they're like moving relative to each other, and eventually so much pressure occurred that finally it breaks. It would be like, I don't know, maybe like an elastic band that you keep pulling and pulling and pulling, and eventually it snaps. Does that make sense as an analogy? Okay. And so deep underground you have the focus. Okay. Now what's going to happen is from the focus, waves are going to get sent out in all directions. Where is the closest to the surface? Well, literally right above it would be the shortest wave you could have, directly above it. And that is called the epicenter. And so the epicenter of an earthquake is literally the first place on Earth that you're going to get hit by waves. First the P waves, then the S waves, and then finally the surface waves. And so it's going to take a little while for all those waves to get to the surface. Keep in mind, those waves traveled about 14 kilometers an hour. So if you were 14 kilometers under the surface, it would take an hour for them to get there. That makes sense? So it's going to take a little while for these waves to get there, but eventually these waves will absolutely rock the epicenter line. Okay. But is the epicenter where the waves originated? No. The focus is where they originated underground. This is just the first part you're going to hit. The problem is that the waves are also going to hit over here, and they're also going to hit over here, and they're also going to hit over here. Right? Now, the further away you get, the less dangerous they are, right? Will earthquake waves arrive in southern Alberta? Yeah. But like they're not really that noticeable for us. You know what I mean? Let me go back to this last slide here. So the words I need you to know were focus, which is underground where the earthquake begins. The epicenter is the location right above the surface. And subduction is basically where the two plates are moving with relative to each other. And eventually one of them tries to go on top of the other plate. It may start forming mountains slowly over time. And that burst finally causes the shaking to occur. And that's my lesson. So I'll let you write down some stuff, and then I'll do a quick verbal summary, and then we can call her a day, and hopefully I can give you guys a little bit of work time today still. Okay, so quick verbal review. Maybe just try to listen while you're writing stuff if you are. Yesterday we talked about how old we believe Earth is. Today we're talking about what we believe is inside of the Earth. And again, it's challenging. We can't go there. Right? It really has to do with earthquakes. That's really the clue we have. There are two types of waves. There's the push P waves, and then there's the secondary waves that go back and forth. Because of the fact that secondary waves cannot go through liquids and gases, on the opposite side of the Earth, when they don't register S waves, we think there's liquid inside the Earth, which actually makes sense because we know that there's like literally liquid lava, magma inside the Earth that can eventually cool and form rocks, especially after volcano erupts, right? So that actually wasn't overly surprising. Also, based on the way that the waves kind of bend as they go from one layer to the next, that's not kind of also a clue for us. So that's why the belief is the inside of the Earth has a core, then there's a liquid magma layer, then you've got the mesosphere, the asthenosphere, and the lithosphere, different layers of crust, basically. Now, that crust doesn't actually stay in one spot. We actually believe that it moves around a little bit. And as it moves around, deep under the Earth is the epicenter. No, sorry, is the focus. And the focus is under the Earth where the two pieces are basically trying to crack compared to each other. On the surface of the Earth, the shortest place above it, that's the epicenter. And that's really where the most danger is going to be. Now, based on this evidence, that's how we believe that we know what's inside the Earth. So we talked a little about some other random stuff along the way, but that's basically the concept. So, you guys have any questions? Okay. I know there's not a ton of time left, but you guys have about 15 minutes or so. I'd highly recommend take a look at some of the questions on the assignment and just do them right now while we finish talking about them. Because I'm sure one of them is like, tell me what S waves and P waves are. Or one of them is explain what subduction is. Okay? So if you want, I'll give you a hand with this as well. But try not to waste the last 15 minutes.